Hi guys, welcome to the video about Ellinghan diagram about these feasibilities of the reactions, right? Now this picture here, the diagram here, the graph here is actually an Ellinghan diagram. So you can see a lot of complicated lines crossing over and different types of reactions here. Now, what is the purpose of having Ellinghan diagram? So Ellinghan diagram is to propose or to show the nature of a chemical reactions over a temperature range. All right, as you can see on the x-axis is actually starting with 0 Kelvin all the way to 2400 kelvins from this graph, and then on the y-axis is actually the Gibbs free energy. I'm sure by now you know what is Gibbs free energy. Gibbs free energy is a value, whether it's positive or negative, to tell us that a reaction is spontaneous or not. All right, let's do a revise here. When the Gibbs free energy is negative, then the reaction is spontaneous. When a Gibbs free energy is positive, the reaction is non-spontaneous. All right, again from the diagram, from the graph here, you can see on the y-axis all the value givens are actually negative. So that makes sense. You see, all these reactions are actually a spontaneous reactions. That's why they have a negative Gibbs free energy. But then why certain lines are actually showing negative gradients, certain lines are actually showing positive gradients over a range of temperature? See, while temperature increases, what happened to carbon plus oxygen to get carbon monoxide? This reaction, why is it going downwards? Why with a negative gradients? But then for the same temperature changes, for carbon monoxide plus oxygen to get carbon dioxide, it's actually showing a positive gradient. You see that? So they have different directions and different gradients. Why is it so? Okay, so in these videos we're going to learn how to interpret Ellinghan diagram. Okay, and then this Ellinghan diagram is to help us to identify or to determine the feasibility of a reactions at certain temperature range. All right, let's move on. Now this is a much simpler Ellinghan diagram because it's only involved two equations. Right, now basically this Ellinghan diagram is referring to the reductions of iron oxide to form iron solid, like an extractions of iron. You're trying to get pure iron using carbon. All right, it's actually given here. See that? The questions. What is the temperature at which the iron oxide can be reduced by carbon? So you're using carbon as a reducing agent, and you try to reduce iron oxide into iron. Okay, so this is the Ellinghan diagram for these reductions of iron oxide. All right, and how, where do we start? Okay, let's look at that. Now, they're asking for temperature where the reductions of iron oxide take place by carbons. Let's look at the equation first. If I said reductions of iron oxide, that would means this equation here is going backwards, right? Iron oxide get reduced to get iron and oxygen gas. And if this equation is going backward for reduction, what happened to another equations where involve carbon? Carbon is a reducing agent, right? So this equation should be going forward, which indicates oxidation, because when a reducing agent, they must undergo oxidations. All right, does it make sense? So I have iron oxide as a reactant, carbon as a reactant. One undergoes reduction, one undergoes oxidations. Now this is what happened. All right, and how do we determine the temperature for the reductions? Okay, can you see the two lines having an intersection here? Right, now intersection points will give us a temperature value. So roughly 500 is about 5, 6, 7, 700, about 600 Kelvin. So the intersection of these two lines is giving us a temperature of 600 kelvins. And that's not the answer yet. When they ask what is the temperature at which iron oxide can be reduced, so this is the temperature where Gibbs free energy equals to 0. Still remember from a previous video, when Gibbs free energy equals to 0, meaning that the equations or the reaction is at equilibrium. So which means they have both products and reactant. The reactions are not 100% visible, and the reaction is not 100% not visible. You get what I mean? It's in between. So here they're asking a temperature at which iron oxide can be reduced. They are referring to a temperature at which the reaction is 100% visible, which means they don't want to look at equilibrium. They want to look at a complete reactions, a fully visible reactions. So what temperature would it be? Would it be more than 600 or less than 600 Kelvin? So basically we try to give a range of temperature. More than 600 Kelvin, the reaction will become highly visible, or less than 600 Kelvin, the reaction becomes not visible. Okay, now first we identify the intersections, and then we get a temperature of 600 Kelvin, and that indicates the Gibbs free energy equals to 0 at equilibrium. Now we need to identify whether more than or less than 600, the reaction, the reductions of iron oxide becoming visible. So how can we do that? We can use the equations to do this. All right, let's see. The equation is Gibbs free equals to enthalpy change minus temperature entropy. So this is the equations, right? Okay. So we want to know what is the Gibbs free energy for these particular reactions. Here. So what is the Gibbs free energy for this? Now, since this reaction is going backward, all the value here is becoming positive because it's the reverse. Make sense? And if let's say I want to know, okay, what if more than 600 Kelvin? So I just choose any temperature more than 600, let's say from here, 1005. I'm going up any random value up to here. And then I'm going to extrapolate it to the x-axis, to the y-axis. And what is the value here? Roughly 320. So it's a positive 320. That will be the Gibbs free energy of these reactions at 1005 Kelvin, which is above 600. Okay, that's the first step. Second step, we look at the second equations here. Again, we chose to check more than 600, hence we choose the same. Let's say for example 1000, okay, make it 2000, different temperature. Okay, and then we try to all the way move the line, extrapolate to the y-axis. And what is the value here? It's roughly 420. Okay, but then still remember this equation is going forward, so here no longer positive. When they are going forward, meaning that they are following the graph, they're following the directions of the reaction given, so all the value here are actually negative, hence your value here is negative 420. So this is the Gibbs free for these oxidation reactions, and that's the Gibbs free for these reduction reactions. And what is the difference between these two? That will give us, and that will tell us whether the reaction will be visible or not at temperature higher than 600. So negative 420 plus with positive 320, right? Try to get a difference between them, and then you will definitely get a negative value. Negative hundreds. So overall Gibbs free change is negative 100 kilojoules per mole. So what does it tell you when you have a negative Gibbs free above 600? The reactions is visible, right? You get a negative values when the temperature is higher. So therefore, the answer for this question is, what is the temperature at which the iron oxide can be reduced? Above 600 Kelvin. That will be your answer. Okay? So let me repeat the same thing again. All right, let me erase everything. I repeat the steps for you. Number one, first we check I have two equations here. All right, and then we check iron oxide reduced by carbon. So this iron oxide is the reactant, reduced by carbon, carbon is the reactant. Hence, this equation, since the reactant is on the right hand side, this equation is going backward for reductions. And the box is on the left hand side here for carbon, hence the reaction must go forward, and that's oxidations. That makes sense, right? It's based on where the reactant is. So we have identified whether reductions or oxidation. Then we have to check the Gibbs free energy at the intersection point, which is 0. So this is the intersection, and at this point the Gibbs free equals to 0, and check what is the temperature here. The temperature here is 600 Kelvin. That's not the answer yet, because 600 Kelvin will just be nice at equilibrium. The reaction is just at equilibrium. So we want it to be 100% feasible, hence we have to check whether it is more than or less than. Which one is the better temperature? So we can choose whether you want to check more than or less than. Just now I show you more than, right? Let's say if you choose to check a temperature less than 600. So let's check 500 then. So I'm going for the iron oxide equation first. So 500 move up is less than 600 obviously, and then we go all the way to the y-axis, and it's about 580. Since these equations, the iron oxide equations, is going backwards, so the value here is not negative but positive. First done. Next, I'll use the same temperature all the way up to the carbon equations, and the carbon equation is going forward. Hence, the value here is following the negative value given on x-axis, which is 410. About that. You see that? So I got the Gibbs free energies for both. One forward, one backward, one oxidation, one reductions. And then we try to get the difference between them. So the difference will be 580 minus 410. You will get a positive value. So the overall Gibbs free change for these reductions, for these reactions, is a positive value when the temperature is less than 600. It will be the same when you check the temperature at 400, check the temperature at 300, or even you check the temperature at 0. You will always get a positive, and even more positive for the Gibbs free change. So from here we can make a conclusion that when the temperature is less than 600 Kelvin, the reactions is not feasible. It's non-spontaneous. So the reduction of iron oxide by using carbon is impossible at a temperature lower than 600 Kelvin. That would mean the answer is more than 600. Because it's either way. If less than 600 is not feasible, more than 600 will definitely giving you a feasible reactions, will definitely giving you a negative Gibbs free change. You get what I mean? So these are the steps used to analyze an Ellinghan diagram. Alright? Okay, that's it. This is a short video to show you how to do questions deal with Ellinghan diagrams. Of course, more example will be given in OL, and you have to try it on your own. Alright? Thank you for watching. I'll see you in the tutorial sessions.